If you have a little information in your mind about the periodic table, let's go into what we call an intermediate look at the periodic table, refining chemical structure and periodicity. And we're going to ask the question, why do atoms gain and lose electrons in very predictable numbers? So we did a conductivity lab, and what we did was, this is a vernier lab, you find the conductivity of 3 different salts: sodium chloride here on the bottom, and magnesium chloride in the middle, and aluminum chloride at the top. You add 1 drop at a time and track the conductivity. As you can see, you get very even uses of the data, giving you lines that go through 0, 0 and have different slopes. And the slopes are given here. And as the number of chlorines increases, you would note that the slope of the line increases. And so the conductivity goes up faster with the ones that have larger number of chlorines. Our interpretation of that is that the sodium chloride dissociates to charged particles called ions that enable the water to conduct electricity, and the more salt you add, the more ions there are, the higher the conductivity. Magnesium chloride must dissociate more because it has more atoms, because it's got a steeper line, and the aluminum chloride dissociates even more, as you can see the steepest line here. So more ions, obviously, in that latter salt. We then interpret the results with a dissociation equation showing the solid sodium chloride breaking up into aqueous sodium and chloride ions, then the magnesium chloride breaking up into magnesium and 2 chloride ions per magnesium, so that's a higher number of ions, higher conductivity, and the aluminum chloride breaking up into a total of 4 ions in the water. And of course the conductivity would be highest for any given number of drops. Now, with our understanding of ionization, the making of ions, we now look at the periodic table. And we see that the metals are able to ionize, that is, lose electrons. Sodium loses 1 electron to become Na+, that's the charge. Well, we look at that and we see, oh, it's got 11 electrons as a metal, but only 10 as an ion, and therefore it's lost 1 electron to get 10 total electrons. We then look at magnesium and see that it has 12 electrons, and when it gets its 2+ charge, that it's lost 2 electrons and therefore again has 10 electrons as an ion. And finally we look at aluminum and see that it has 13 electrons, and to get to a +3 state it has to lose 3, and again it has 10 electrons as an ion. You may want at this point to turn off the video and think about what seems to be happening, or discuss what's happening to all these metallic atoms as they ionize. Dmitri Mendeleev gave us the periodic table. He had a theory that was 50 years ahead of its time. Now, he knew nothing about atomic structure, had no knowledge of protons or electrons, had no idea that there was a nucleus. He knew none of the noble gases. He was missing then several dozen elements in his table of atomic masses that he was using. But he saw that as the atomic mass of atoms increase, the chemical properties are repeating in a predictable manner. He gave us this periodic table. That's how it was published originally in the German scientific literature. His theory is that, again, as atomic mass increases, the chemical properties of the elements recur periodically. So, instance, magnesium, beryllium, and calcium all react with weak acids, and they form compounds with chlorine in the ratio 1:2. The fluorine, chlorine, bromine, and iodine are reactive nonmetals, and they combine in similar proportions with the same metal. So for instance, if there's sodium chloride, NaCl, there's also sodium iodide, NaI. Sodium, potassium, and to a less extent lithium are soft metals, very good metals. They react with air, they react with oxygen, and they react with water, all in similar ways, and they form compounds with similar chemical properties and formulas. Mendeleev put his table together, and unlike Lothar Meyer, who had another table, he left holes where he didn't see an element that fit this pattern that he had discovered. So where are his holes? Well, first of all, he left one at about mass 68. He called it Eka aluminum. And then he left one at 72 right next door that he called Eka silicon, because he didn't see anything with those atomic masses that fit in with the chemical properties of their column. Within just months, the folks in Germany and in France had discovered both elements, gallium and germanium. And if you look here at a Wikipedia chart that shows Mendeleev's predictions on the left for both of these elements, and the actual properties of the elements as discovered just a few years later, amazing correspondence. In other words, his theory had made accurate predictions. The columns in Mendeleev's periodic table represent families with similar chemical properties, and this is how we have structured the periodic table ever since. A few years later, Moseley came along in England. He was a student of Rutherford's, and he found, no, it's not the atomic mass that is the measure by which we see the increasing and periodic property repetition. It's the atomic number, the number of protons in the nucleus, which of course is equal to the number of the electrons in the nuclear atom, in the neutral atom. Moseley also knew the inert gases, the noble gases, and he put that in as well. And he generated the periodic table in its basic modern form. Now we go to hydrogen. Hydrogen's unique. It's the only one with just one electron and proton. It is the most common element in the universe. It's unlike all the elements, so it really doesn't belong with the alkalis, even though you often see it put right on top of that group 1. It isn't a metal. It doesn't form ions like lithium and sodium. And as a gas, it comes in packages of 2. Hydrogen is H2. Moreover, hydrogen almost never gives away an electron. It shares its electron. And therefore it really is unique and belongs in a class by itself. Helium is the first noble gas, element number 2. It has a low energy and is chemically unreactive. We know of no chemical compounds that it forms. It was the first of the noble gases, and it was discovered by absorption spectrum in the sun. It is now mined in deep wells, natural gas wells typically. Helium has 2 electrons. We look at this group that helium is in, and we call them the noble gases. It is very difficult to get noble gases to react. They're in a low energy state. It's very difficult. Group 1 is called the alkali metals, and they form compounds with chlorine like NaCl, KCl. They seem to be losing 1 electrons. And let's note that the number of electrons of the ion that is formed is just 1 less because it's lost an electron. Lithium loses 1 electron. It's got 3 to begin with. It loses 1, and then it's chemically unreactive, very much like helium. So at 2 electrons, it seems we've got a very unreactive situation. The lithium ions are not reactive. Now it's true, lithium ions don't turn into helium gas. They're not a gas, they're in salts, but they behave chemically like noble gases. They don't react. Group 2, right next door, is called the alkaline earths. They form compounds with chlorine like BeCl2, MgCl2. It appears that they lose 2 electrons. When these lose 2 electrons, if you see, beryllium ions look like helium, magnesium ions, Mg2+, look like neon. They have electron structures just like the noble gas below them. They don't react. Group 3 begins with boron, but boron is not really a metal. But aluminum, as we know, loses 3 electrons of its 13 and has an electron structure just like neon, a noble gas, and it's non-reactive. It appears that when you have a metal, it loses electrons in a quantity that makes them act chemically like the next lowest noble gases. That ion that results is a lower energy, we could say stable ion. Now the electrons that metals lose are typically picked up by nonmetals like oxygen, which apparently gets the 2 electrons lost by magnesium because its formula is MgO. Magnesium loses 2, oxygen picks it up to form an oxide ion. And the group 17 groups seem to pick up only 1 electron, then they chemically look like the next higher noble gas. Fluorine looks like neon, chlorine looks like argon once it's formed an ion. Very low energy, very non-reactive. We also have the transition metals that are in the middle. We will talk about them quite a bit this year, and especially in AP chemistry. The transition metals often form colored hydrated salts when they are ionized. This is a quantum effect you'll study in AP chemistry. Remember, each group of the periodic table, the up and down, so to speak, the columns, react similarly. And as you move from left to right in a period, a row, chemical properties start off metallic, and by group 7, they're all nonmetallic. Metals lose electrons, and that makes them appear as ions like noble gases. Nonmetals gain electrons. It's very important to remember the noble gases will not react at all under normal circumstances.